Physics tells us that the electric field is kq over r squared times the r vector divided by r, where everything is the same as it is for the gravitational field, the r vector and so forth, but the source is not a gravitational object, the source is a charge. And instead of the gravitational constant g, we use the electrostatic constant k. Now k is 9 times 10 to the 9th Newton meter squared per Coulomb squared, and it's equal to 1 over 4 pi epsilon naught, if you like epsilon naught. So you can easily calculate epsilon naught from k. But this is just totally analogous to the gravitational field of a point-like mass centered at the origin. So we want to calculate the flux through a sphere of radius r centered at the origin due to this charge q located at the origin. Well, here's our electric field, kq over r squared times the r vector divided by r, where r is just a vector from the origin out to this point on the sphere, and it's radial, which means it's parallel to the outward normal, which means that since it has a uniform magnitude everywhere on the sphere, because everywhere on the sphere r is the same, and right there is the magnitude, kq over r squared, whatever r happens to be, that's it for the entire sphere, it follows that the flux is just equal to the magnitude of the electric field multiplied by the area, which is just what? Well, the electric field is this. The area of the sphere is 4 pi r squared. If I multiply kq over r squared by 4 pi r squared, I get 4 pi kq. So there is my electric field. Magnitude, well, this is the magnitude of the electric field. Multiply that by the area, we get this. And that would be the surface area, the flux of the electric field through the surface. Okay, so there's a little redundancy right here, but that's okay. Not difficult to understand and prove that this is the case. So the flux of the field, and I'll just call it the E field, through any sphere, then has to be 4 pi kq. Why is that? Well, that's what I want to show here. Okay, so let this be any sphere, okay, centered at the origin. Now it turns out this could be any shape at all surrounding the origin, but that's okay. We'll make it a sphere for right now. So what we have is here a tiny sphere about the point with charge q. So we got a charge q here. Okay, again, I should be a little more specific about what I'm saying here. It's clear from the statement that you have on paper, but through any sphere, I'm reaching a little bit. Any sphere with q at its center, well, certainly for any sphere concentric with the origin when q is at the origin, the flux should be 4 pi kq. So let's make the argument again. So there's a tiny sphere about the point with charge q. Assume this is the origin, but it doesn't really matter. I've got a point mass m because I originally did this for gravitational field, and it turned out that wasn't a good idea because the gravitational field is always inward. And we didn't want to deal with a negative sign. Okay, well anyhow, tiny sphere about the point with charge q. And then this is any sphere about the point charge q. Any sphere actually enclosing the point charge q. Everywhere between these two spheres, the divergence of this electric field is 0. And that's very easily proven. We've proven that for this type of a function, for this function. Very easy to prove. Divergence is 0 everywhere except at the position of the point charge. So certainly, if you look at the region between this tiny sphere that encloses the charge and the sphere that surrounds everything, the divergence is 0 everywhere inside here. So if you make a surface out of this outer sphere and this inner sphere, and that surface is the boundary of the region between these two spheres, the flux through that boundary has to be 0 by the divergence theorem. Well, here we have a picture. We have an outward flux on this sphere. Well, I'm sorry, well, we do have an outward flux. Actually, Q could be negative, so it could be an inward flux, but let's not worry about that right now. Okay? These are the outward normals. So you have outward normals around the outer sphere. Those are the normals that point from the interior of this region out. Remember, the region is the region between the tiny sphere and the larger sphere, right? Well, what points out of the region through the surface of the tiny sphere? Well, that's toward the center, isn't it? These normals are toward the center because, remember, it's always the normal that points out of your region. Then the flux through here is going to be negative 4 pi kq because, of course, the flux going this way through the sphere is 4 pi kq. If this flux is negative 4 pi kq, the total flux through the entire surface of this region is 0. Well, that means that the flux has to equal 4 pi kq through the outer sphere. Flux through the outer sphere is 4 pi kq. Well, it's not a completely rigorous proof, but it's a pretty good indication. It's very close to being a rigorous proof that any sphere enclosing this tiny charge Q will have a flux of 4 pi kq. Okay, the flux through any sphere enclosing this charge Q is 4 pi kq. And that doesn't apply just to a sphere. This purple region, this any old blob containing this charge, we could make the same exact argument. The tiny sphere, the outward flux is 4 pi kq. Any tiny sphere surrounding this charge. Between that tiny sphere and whatever surface this is, divergence is 0 because the divergence of this function is 0 everywhere except where r equals 0, and that would be at the charge. Okay, so between here and here, we don't have the charge, so divergence is 0 everywhere here. So, again, the flux through this tiny sphere is negative 4 pi kq. The flux through the entire region consisting of this outer blob and this inner sphere is 0, so the flux through the outer blob is 4 pi kq. That's Gauss's law. Okay. So there's the statement, let the boundary consist of the inner and outer sphere, or the inner sphere and the outer blob, the outer region. Divergence theorem tells us the total flux is 0, so the flux through the outer sphere or the outer region is 4 pi kq.